Alright, 3, 2, 1, let's go. Alright, so welcome to another exciting Math 2070 online section video. Alright, so today we're going to talk about one of my favorite things, good old linear transforms. So let's start off by getting all on the same page. What we're talking about today are functions, and functions are a very essential part of mathematics. So, maybe inarguably, or at least is a very good candidate, e to the x is an incredibly important function for a wide variety of reasons, and it's great. And note the general format here. I'm using the symbol f to denote the function, and the function's property is you give me an input, and I put it up in the exponent with the natural base down here. Right. And notationally, the way functions will be announced in this course will be as follows. Pretty standard notation, where f denotes the symbol I'll use for the function. A will denote the set of admissible inputs x, and B will denote the codomain, which is where the outputs f of x live. Right. And as we've already set up, the place that we're going to hang out with the most is the good old Euclidean space, the collection of real numbers and a list of n real numbers. And so, naturally, the functions we'll look at in this course are going to be between these two. So, for example, a function from R2 to R2 can be defined as follows. An element of R2 is a vector consisting of two things, x1 and x2, and my function here takes the two inputs and gives me the two outputs, where in the first I'll take the first and square it, and in the second I'll say I don't care and just make it 1. Alright, so here we see something a little bit more interesting going on than our usual functions we saw in calculus, where there was one input and one output. Here I have one input, but the input has multiple pieces, and some of those pieces may or may not appear in the outputs. Quite interesting. Alright, so this is what we're going to be hanging out with, and today our focus will be on a very specific type of mapping. A linear transformation is a mapping from Rn to Rn, m to n, note they don't need to be the same, and they satisfy a very specific set of rules here. Now, of course, we can just read these. T of cx is c of t of x, and t of x plus y is t of x plus t of y. But, right, we don't want to just read just plainly what the symbols are. We also want to just sort of read, mathematically read this. Right, use our mathematical literacy. This here is telling me that my mapping respects scaling. The scaled input yields a scaled output. Right, and similarly the mapping respects addition. A added input yields a added output. And note that Euclidean space here, the fundamental operations of scaling and adding, these are the mappings that respect these. So, right, it's more than just reading what the equation is. This is communicating a pretty big idea to us, that I'm looking at functions that respect the operations associated with the things we're looking at. Right, and we saw this stuff before in calculus, right? Derivatives are linear. The derivative of a scaled function is a scaled derivative. Integration is linear. Integrate a sum, you get the sum of the integrals. Right, that's our favorite sort of snow clone in mathematics. The x of the y is the y of the x. Now, before we get some examples and non-examples of this, let's quickly point out two immediate properties that such mappings need to have. And this will help us sort of immediately eliminate functions from being linear. The first property is that linear mappings have to fix the origin. They have to send 0 to 0. And this is easy to see from either of the hypotheses here, but I think it's most easiest from the additive one, because t of 0 is t of 0 plus 0. 0 plus itself, as we noted, doesn't do anything. And my mapping respects addition, so it pulls apart, and thus I'm allowed to cancel and get t of 0 as 0. You can also use the scaling where you just scale 0 by 0 and then pull 0 out. But I think the scaling one reveals another property of linear transformations, which is that negatives get pulled out. And as we noted, negative x is x scaled by negative 1, and you can just pull out the negative 1 like that. Neat. Now, note, the origin is fixed, and also this tells me that my linear mappings have to be odd mappings. So if you remember, a odd mapping throws negatives out, and an even mapping, it destroys the negatives. So here we see linear mappings have to fix the origin, and they also have to be odd mappings. So it's pretty easy now to immediately throw out functions that are not linear. So for example, the first function we talked about here from R2 to R2, this fails to be linear for a variety of reasons, but a quick and easy one is that it clearly does not send 0 to 0. 0 will get sent to 0, 1, failing to be linear. All right, so here we have an example of something that is not linear, a non-linear mapping. And whenever you make a math definition, you always want to do two things. You want to show me something that works and show me something that doesn't work. That makes it a definition. If everything worked, that's an axiom, and if nothing works, then that's garbage. So now that we have a example of something failing to be linear, let's get an example of something that is linear, and the essential, and as we will learn in the next video, only possible linear mappings are matrix multiplications, right? So given an n by m matrix, so note the size of it, if I take our vectors from Rm, I can multiply those by our matrix A, and note that would create an element of Rn. And here, note how we've defined it. Before, when we've defined our mappings from Euclidean space, we sort of listed each individual component. Note, we don't need to do that here. You can just give me the vector x, and I can multiply it by A. We have this nice compact notation for this. And this mapping is super easy to see that it's linear because I already told you this is linear. We talked about two properties of matrix multiplication, and those two properties that we talked about were I can pull scalars out and I can distribute A. And both of these together then reveal to me that my mapping is linear, because if I feed in a scaled input, I get the scaled output, and if I feed in a summed input, I get the outputs summed. Beautiful. So there we go. Now we have a plethora, a profusion of linear mappings, matrix multiplication. And our mappings that we may be looking at sometimes will have a hidden matrix. So for example, here is a function from R3 to R2, and it may not immediately look like it, but this is indeed a linear mapping, and it's got a matrix hidden inside of it, because if we really looked at what I have here, I have, hey, 2 on x1, no x2, 1 on x3, 1 on x1, 1 on x2, and 2 on x3. And indeed, letting A be precisely the matrix whose coefficients correspond to these suspiciously linear-looking expressions, I indeed get our matrix for this. And note that this tells me now that T is a linear mapping. So sometimes I can actually communicate a linear mapping to you without explicitly giving you the matrix. I can just give you a collection of linear expressions like this. Nice. So this will be something we'll be doing every so often, where we sort of just announce a linear mapping and don't explicitly give us a matrix for it. And as I've already sort of hinted at, I've been kind of letting the cat out of the bag here. Seems like the only way you could make a linear mapping is with matrix multiplication. Now, it doesn't immediately seem why that's true, but think about it for a little bit. What's another way of making something linear? Well, keep that in mind, because in the next video, we will indeed answer this wide question and find out that, indeed, for any linear transformation, there is a matrix associated with it. And thus we find that while linear mappings are very interesting, they are maybe limited in scope. They have to be matrix multiplication. But that's a good thing.